Hold on. Yes, and we're live. Excellent. Oh, man. I have this song stuck in my head, and I really hope you can appreciate it. Do you guys know the moon theme from DuckTales? Thank you. Right? Stuck in my head. Just saying. Y'all don't appreciate DuckTales. Just saying. You should. It's a good show. Anyway, back to this. The finale was last night. No, I'm going to stop talking about DuckTales. I could really go on the whole day about it. But anyway, a couple of things. Number one, yes, you did have something due for me today, but as I put in the directions for that thing due today, if I can bring up the directions just to read them verbatim, I said, in preparation for Tuesday, March 16th, I want you to complete the attached review. This will be considered a homework, meaning I'm not grading on correctness. Just don't look up the answers. Challenge yourself to get these things done. I expect that you will attach a picture of your work you did to these problems in preparation for Tuesday, because we will be reviewing them. I have been reviewing this unit methodically because of the importance of hypothesis testing. And yes, that is what my plan is for today. I would like to go over those problems in great detail. Because I am gearing you up. I am gearing you up for a major assessment. Now, this major assessment will cover Unit 5. In the textbook, the stuff that we've been covering, just to be very clear about Unit 5, I'll read you the exact titles to Unit 5. Chapter numbers are a little bit hazy because they've changed books recently. But yeah, Chapter 5. Unit 5 is chapters 17 through 21. Chapter 17 started with sampling distribution models. Then we went to confidence intervals. And then for the last 3 chapters, and yes, it's 3 chapters so far, we've been covering hypothesis testing. That's probably why it feels like we've been doing nothing but hypothesis testing for the past several weeks, is because it's 3 chapters in a row, and it will be the next several chapters after this unit as well. Just different forms of hypothesis testing. So that is my goal. I would like to review for said major. I plan on assigning the major probably by the end of this week. Probably Friday, give or take. And then, of course, you'll have a sufficient amount of time to get that thing done. Just as a heads up, and this is a heads up for y'all to have your Chromebooks charged and ready to go. I mentioned this last week. I'm going to mention it again. I might be out on Thursday. I say might. Right now, it's probably roughly 50-50 shot. If I am out on Thursday, there will be something assigned. I can't even think of the phrasing. When I schedule an assignment, what is that called? Like, I don't know. Say again? Well, not posted. Like, I won't be posting it in the moment. Like, Google Classroom will be posting it. Like, whatever it's called. You know what I'm saying? I'll have something scheduled to be posted by the time class begins on Thursday. So you need to make sure you have your Chromebooks on Thursday, regardless. Like I said, right now it's a 50-50 shot, but I'm kind of aiming for not being here on Thursday. I'm getting the second vaccine shot on Wednesday. And people have told me that it's a real punch in the face. And they suggested, hey, you might want to consider taking Thursday off. I'm like, all right, whatever. So I actually talked to somebody who got the second COVID shot, and they said, yeah, the next day I slept in until about 10 a.m. I'm like, okay, whoa, all right. I might want to consider taking that day off. I don't know. We'll see what happens. And then I'll have more times to watch DuckTales. See, I brought it all back together. It's just one cohesive circle. Anyway, so what I'm going to need from you, I'm going to suggest that if there is something that you want to write down in regards to, I might need to remember that or need to study that in regards to the major that's coming up, okay, that's up to you. But what I am going to ask is whatever work you have for the review that you guys just did for me, have that out so you can compare your answers to what I'm getting up here. And if there are questions, of course, we can knock out those questions as well. Because I want to make sure that we're all on top of this information. Now, as I make the walk over to my desk over there, if you would, I see one so far, but if you would leave a comment in the chat, you virtual students, that would be fantastic, and I will check that later. Make sure you leave a comment in the chat. this is for later as well. Awesome. There we go. Okay. So I have a physical copy of the page that I had for you guys. I mean, obviously, I also have it right here as well. But I figured, why not just have the physical copy as well? So I have that right here. Chapoom. And I can try to zoom in as best I can. Of course, for those of you online, I know this may be a little bit difficult to read. Obviously, you do have the PDF available through the latest Google Classroom assignment, so you don't have to strain yourself trying to look at this thing. Here we go. Dolphin births. A state aquarium that have dolphins, a state has 2 aquariums that has dolphins, with more births recorded at the larger aquarium than at the smaller one. Records indicate that in general, babies are equally likely to be male or female, but the gender ratio varies from season to season. Which aquarium is more likely to report a season when over 2/3 of the dolphins born were males? Now, they don't really give you much in terms of numbers. They really don't give you much in terms of numbers. 2/3 is one number that you could potentially work with. 50-50, that you have to, or they're assuming 50-50 gender in dolphin babies. The only real thing that they tell you is that one aquarium is larger than the other. I guess the assumption being that the larger aquarium has more dolphins, so to speak. So I'm just going to write out some general notes for myself before I come to a conclusion here. So let's call it the sample size of the larger aquarium, according to this, is larger than the sample size of the smaller aquarium. Again, this isn't necessary to write down for an AP response. I'm just doing this so I can conceptualize what's going on. They say 50-50, so yeah, that's the expected is 50-50. Which is more likely to, okay. Over 2/3 okay, got it. They're basically saying that you're expecting 50-50, but it is entirely possible for one of the aquariums to have a birth ratio between male and female where 2/3 of the dolphins were born male. It is possible, although unlikely. See, because there is a term. Oh, what was that term? We learned it during this unit, where when you take a sample, there is a natural variation from the expectation. Do you remember? No. The law of large numbers is just basically that as time goes on, the experimental probability will approach theoretical probability. Or actually, no, we could use that, couldn't we? How about this? What do you mean by the law of large numbers? Explain. That's a better way of looking at it. Okay. The term I was going for was sampling error. There's a natural variation. And variation occurs more often the smaller the sample size that you have. Although you're looking at it from the other side of the coin, which is still correct. So you could answer this thing in one of 2 ways. You could answer it from that perspective, meaning, well, according to the law of large numbers, the larger the sample size, the more likely that our sample proportion will approach 50-50. Thus, the smaller aquarium is more likely to have a result of 2/3 male. Or we could look at it from the other perspective, meaning that, well, variation, I guess, no, it's kind of the same thing. Variation happens less the larger the sample size. Again, it's like two sides of the same coin. Or the smaller the sample size, the more likely we are to have larger variations. I'm going to read you the actual response, or the suggested response, but everything that we just talked about is perfectly valid to talk about in regards to this. I could say, actually, I'm going to write my thing down first. I'm going to combine it with a little bit of what he said too. Okay. The larger the sample size, the larger the sample size, the more likely the proportion will be closer to 50-50. So which aquarium is more likely to have 2/3? Thus, the smaller aquarium is more likely to have a season of 2/3 male dolphins. Again, that's just something that I would write out, just kind of like shorthand. Again, let me read what this thing says. It says the smaller aquarium would experience more variability in the season percentage of male births. We would expect the larger aquarium to stay more consistent and closer to 50-50. Yeah. I mean, in general, again, you can look at it from either perspective, but we know that the sample size of the larger aquarium is larger than the smaller one. Oh, dolphins. Godless killing machines. Number 12. Approved rating. A newspaper article reported that a poll based on a sample of 1150 residents of a state showed that the state's governor job approval stood at 58%. Okay, I'm just trying to take that all in. What I typically like to do with free response questions is I like to take them a statement at a time and try to gather my thoughts on that one statement before I read the next one. That's typically my MO when it comes to free response questions. It may not be a strategy that works for you. You may be someone who likes to take in the whole problem and then try to decipher individual pieces. That's up to you. It depends on what strategy works best for you. But for me, I'd immediately be like, okay, sample size is 1150. In that sample, they reported an approval rating of 58%. So P hat would be 0.58. And I think that's all the information I get from the first statement. They claimed a margin of error of plus or minus 3%. Oh, here we go. Margin of error is plus or minus 3%. And immediately, instead of 3%, I put it at 0.03. Then they want to know the level of confidence. Here we go. Here we go. That should be enough information for us. We do not know the actual job approval rating of this governor. We only know the approval rating through the sample. Okay. They claim a margin of error of 3%, meaning that they actually conducted the confidence interval. They constructed a confidence interval, and they got 3% margin of error. If you remember, your margin of error is everything after this calculation. There we go. Your margin of error is everything after that calculation. It's the plus or minus z star times the standard error, which is the square root p hat q hat over n. Okay. Nice. 0.03. I'm going to ignore the plus or minus because that basically cancels out from each side. square root 0.58 what is that? 42? Cool. I just want to make sure. Divided by 1150. There we go. That's my setup to the problem. By solving for z star, I'm going to figure out exactly what the z-score is. The z-score that they, or the z-star that they used in order to construct the confidence interval. Now, whatever I get for the z-star is not my final answer because they want the level of confidence, meaning that they want a percentage. They want to know, was I 95% confident? Was I 97% confident? What percent confident was I? I don't know. Let me take my calculator real quick, and let me do the following calculation. That should work. My z-star was 2.061 or some junk like that. 2.061. Yeah, that one actually was a pretty straightforward calculation. Now, again, not my final answer. If you want to visually conceptualize what the heck is going on with that z-star, if you want to visually conceptualize what the heck is going on, sometimes it helps to see, and you know, I'll draw this on a separate piece of paper because I want to have enough room to do it. Sometimes it helps to see the normal curve here. There we go. I have no idea what the percentage is at the moment, but I do know that it is going from a z-score of negative 2.061 to positive 2.061. And if I can figure out the percentage that falls between those two z-scores, then that will give me the percent confidence that I am, or the percent confident that they were in constructing this margin of error. So, since we're dealing with all these z's and z stars and all this junk, I'm going to go here. I'm going to go to normal CDF. Actually, let me recalculate this real quick. There we go. I'm going to get a little more accurate. You don't have to do it like I just did right there. You really, really don't. I'm going to show you the alternate way that you can do it in a moment. But for me, I'm just trying to be as accurate as possible. Boom. That looks good to me right there. What is that? 96. Technically, I guess you could say 96.1%. Let me see what the thing says here. Well, they even go less. The answer sheet here says 96% right on the dot. And I'm like, it's not 96% right on the dot, but I guess for the lack of a better term, that's the best we're going to get. If you really wanted to go, just typing in whatever numbers you got, negative 2.06, comma, positive 2.06. Yeah, it's still 96.1%. It's still 96.1%. But like I said, once you have that z-star, it helps to visualize what's going on. And if you're going to visualize it, it's like, okay, well, I'm trying to figure out what percent of the curve that I got going between positive and negative of the z that I found. And then from there, I'm going to do normal CDF of those two z-scores to get my percent confidence. Oh, these problems. I don't like that they weren't as accurate as I was on here. But what are you going to do? Stuck pumpkins. Oh, I should bring this down. There we go. Nice. My wife once made an apple pie that she forgot to put. If you've ever baked an apple pie, you know what happens the longer it bakes? Like typically like the apple juice and innards kind of fall over the sides. Have you ever had liquid hit the bottom of the oven? Yeah. So she's baking this pie at 10 o'clock at night. right before Thanksgiving, and my son is asleep, and the smoke alarm starts going off, and I run into the kitchen. I'm like, what is going on? Because I thought there was a fire. And she's like, I forgot to put a pan under the pie, and now there's stuff dripping on the bottom, and there's smoke everywhere. And she's literally standing in front of the oven with a towel, wafting it at like 10 o'clock at night. Like, I don't know what to do. I took a picture of her because I thought it was hilarious. My son never woke up, even though the smoke alarms are going off. We had to open the front door, the back door. It was nuts. Anyway, pumpkin pie. There's no point to that story. A can of pumpkin pie mix contains a mean of 30 ounces and a standard deviation of 2 ounces. Okay, hold on a second there. Again, without reading the rest of it. Let me just kind of think about that statement. That statement, that first sentence, did not say that it was a sample. It did not say that it's like an estimated number or anything like that. It says that a can of pumpkin pie mix contains a mean of 30 ounces and a standard deviation of 2 ounces. That is what they are supposed to contain on average. I believe that they have given us population parameters. I believe that they have given us population parameters when it comes to this stuff. So, man, I would like to label it as such. Okay. Mu is equal to 30. Sigma is equal to 2. I'm assuming that's like the company's like standard numbers or some junk like that. Oh, the contents of the cans are normally distributed. Excellent. Meaning we don't have to show that it's actually normal. We don't have to show that stuff. It actually is normal. Oh my goodness. I don't have to go through that. Okay. What is the probability that 4 randomly selected cans, now we're getting into four in a sample, of pumpkin pie mix contain a total of more than 126 ounces? Interesting. Okay, let's talk about those 4 cans. So I'm going to put a little slash here just to kind of separate that information because I'm just going to keep that for later. But now we're talking about 4 cans, and they want the probability of having the total, what is it, the weight? No, it's just the mix, right? Yeah. A total of more than 126 ounces. Interesting. If I had 4 cans from the store, what is the expected number of ounces that I would be holding? Now, they're asking, what is the probability that I have 126 ounces or more? Ignore that for a moment. What is my expected weight? Again? You expect 120. Yes, absolutely. We would expect 120 ounces. So hold on. The expected, ounces, for the lack of a better term, the expected number of ounces is 120. Yes, that is what we would expect to happen. But what about the standard deviation? I can't just make it an 8. I can't just be like, oh, 2 times 4 is 8. No, I can't do that. Each individual can has a standard deviation of 2 ounces, which means each individual can deviate from 30 ounces. It could deviate, according to that normal distribution, on average by like 2 ounces. What do I do? How do I find a combined standard deviation for 4? Is it fair to say they're independent cans? Yeah, I'd say so. Are they randomly selected? Yes. Excellent. They are randomly selected. That's important because if they weren't randomly selected, then I might argue that there was I couldn't argue independence. Because if I got them all from the same store on the same shelf, what if those 4 cans all came out in a row when the machine was kind of broken? It's possible. I don't know. But since they're randomly selected, it's fair to say that the amount of pumpkin pie mix within the cans is independent from each other. So I have 4 separate cans then. Where's my marker? I have 4 cans. I'm not actually putting that on my paper. Well, I'll put this up top. I'll put it there. 2, 2, 2, 2. That's the standard deviation for each of them. How do I combine all 4? Ooh. Can't just do 2 times 4. I can't just add them all up. Again? Yeah, you do. You do. You want to combine them? You got to go to variance. You got to go to variance first and then convert them back. So ultimately, the combined standard deviation, you would have to square each of them to turn them into variance, then add them all together, then square root them back in order to get the combined standard deviation. So well, you can't always do this in your head, but this one you actually can do in your head a little bit because all of them squared would be 4. Add them all up, you'd have 16. Square root them back, you'd be at 4. That's actually the combined standard deviation here. So hold on. Yeah. There. Come on, little thing. Why are you not working? There we go. Okay. So if I want to combine these things, which by the way, the way that I'm doing this problem is one way. I'm going to show you an alternate way after I finish this one, but we'll get there. So if I'm going to actually find the standard deviation in ounces of the 4 cans, the standard deviation of the 4 cans, it would actually be 2 squared plus 2 squared plus 2 squared plus 2 squared square root. I mean, of course, I could combine all of them and be like, well, 2 squared is 4 times 4 is 16. Square root of 16 is 4. I mean, but since there's only 4 cans, I'm just going to do that. That is the expected standard deviation. All of this information combined leads me to this. Normal CDF. Can't see it. Zoom out. There we go. Normal CDF. 126, comma, big number. Lower and upper limit, 126 or more than 126 ounces. Comma, the expected mean for 4 cans. Comma, the expected standard deviation for 4 cans. I don't know what this gets me. Let me see what happens here. Normal CDF, 126, comma, big number, comma, 120, comma, 4. Sweet. 0.0668. I don't know why I wanted to do that. 0.0668. That's terrible. I'm going to write that. No, I'll just leave it there. 0.0668. Let me show you the alternate way of doing this problem. This is not the only way of doing this problem. Definitely not. We're looking at it for this problem that's up there right now. We are looking at it from the perspective of 4 cans. We are looking at it from the perspective of all 4 cans combined. But what if we were to look at it from the perspective of the average of 4 cans? The average of 4 cans. So let me go back here for this thing right here. If I'm looking at the average of 4 cans, then I can still let this equal 30, because that was the population parameter, if I'm just looking at the average of 4 cans. But if I'm looking at now a standard deviation of the average of 4 cans, square root of n, 4, there we go. The way that this works is by that formula right there. This is a sampling distribution. I'm now looking at a sampling distribution where the sample size is 4. This is just looking at it from a different perspective. But it should work nonetheless. It should work nonetheless. Now, the thing is, I do have to change that 126 now, because that 126 is the combined total that they are looking for. But if I'm looking at that 126 from the perspective of the average of 4 cans, I would actually have to divide them. So now this is a brand new problem. They want the probability of getting an average of 31.5 or more. It's just a different way of looking at the problem. Both ways are perfectly valid. Both ways are perfectly valid. So I'm going to do a normal CDF, parentheses, 31.5, comma, big number, comma, 30 for the average. And I'll just type it in. Oh, technically, I mean, again, you could do that math in your head, but I'm just going to leave it as this for the time being, just for the visual of it all. Let me show that on the calculator. Actually, let me bring up my calculator up here. Let's see here. There we go. Let's see. So here's the first calculation that we did. The first calculation that we did was 126, comma, some big number, comma, 120, comma, 4. That was the first calculation that we did. And you can see the answer right there, 0.0668. But with this new calculation, we can go 31.5, comma, big number, comma, 30, comma, 2 divided by the square root of 4, which, again, clearly I know what that is, but I'm just typing it in for the sake of the visual. Oh, would you look at that? It doesn't matter which perspective you take it from. If you take it from the combined total of 4 cans, which we did when I wrote it on the paper in red, or if we look at the average, the mean of 4 cans. Because for that second part that we did, for the 31.5, we actually used the central limit theorem. We used the fundamental theorem of statistics, the sampling distribution, becoming more and more normal. Sigma divided by the square root of n. That's what we did in that sampling distribution chapter. So, and back here. There we go. It still works nonetheless. Approximately 0.0668. Huzzah! Is what people say. I don't know. All right. Let's talk what most people think of when they think of AP Stat. So, a recent psychiatric study from the University of Southampton observed a higher incidence of depression among women whose birth weight was less than 6.6 pounds than in women whose birth weight was over 6.6 pounds. Okay, again, this is me. This is just my prerogative when I read these things. I like to really think about what information they've given me sentence by sentence. Again, you don't have to do that. If you prefer reading the whole thing and then trying to go back, that's completely up to you. If that works for you, that works for you. I'm just letting you know what works for me. So there's a study. There's a higher incidence of women whose birth weight, not that they had kids, but their actual birth weight was less than 6.6 pounds than in women whose birth weight was over 6.6 pounds. Okay. All right. I can't really write much from that so far other than 6.6 pounds, but based on a p-value of 0.0248, the researchers concluded that there was evidence that low birth weights may be a risk factor for susceptibility to depression. So they've already conducted the hypothesis test, and they've gotten that p-value of 0.0248. Now, again, without reading the rest of the problem, 0.0248, what would you typically do? Would you reject or fail to reject? What would you do? I don't even know what the null hypothesis is, but what would you do? Oh, no. You want me to sing more DuckTales? No, don't shake your head yes. Again, depending on what the alpha level is, which we don't know what the alpha level is, but we assume it's 0.05. You should be rejecting, but I don't even know what the null hypothesis is at the moment. I don't even know what I'm rejecting. I still have to finish reading and then kind of go back. Explaining context, what the reported p-value means. Oh, now this is an important statement. Actually, you know what? Before I stand up, I want you, if you have the paper, I want you to underline it. If you don't have the paper, I want you just to write in big letters somewhere, this. In context. Pretty much since September, I have been harping upon the idea of context. I even mentioned that a previous year's class, they didn't do it, but they suggested that they actually get me a t-shirt that literally all it said was the word context on it, and then no one would get it because they don't understand the context. Ha ha ha, ha ha, ha ha ha. But you need to know what it means in context. Now, I know what a p-value is in general. But I have to construct what it means by the context in this problem. In general, a p-value is the probability of seeing those sample results given that a certain number is true. It's the probability of seeing sampled results or that are in front of you or whatever sampled results were taken, given that a certain null hypothesis was true or that a certain mean was true. But I have to dive back into the problem in order to get that context. So a recent study observed a higher incidence of depression among women whose birth weight was less than 6.6 pounds than in those who were more than 6.6 pounds. Okay. So the recent study, the sample that was taken, observed the result that was in that first sentence. What would be the null hypothesis? What would be a good way of wording a null hypothesis for this problem? That's something that they don't tell you. You're going to have to figure that out. In general, again, I'm not giving it to you in context. I would like to know what you think it is in context. But in general, a null hypothesis is there's nothing going on, nothing to see here, innocent until proven guilty. What do you think? I know what you're saying. I'll correct one quick thing, though. It wouldn't be P in this case. P would be for proportions. It would be mu. But continue.
It'd be like greater than, but I don't know like how.
No, I got you. I got you. I totally get it. Now, they're talking about a higher incidence of depression among women whose birth weight was less and greater than blah, blah, blah. I don't know the mechanics behind it all. And the thing is, you don't have to know the mechanics behind it all. All you need to know is that the mechanics were already done for you. The assumptions and conditions were already done for you. Basically, you just have to visualize, and I'm going to write it out what it could be, but you have to visualize what the null hypothesis was in order to understand this problem, in order to write what you think it is. What were you going to say? I thought your hand was up. No? More DuckTales? Oh, gosh. I'm just saying, if you all are not watching that show, you're not my friend. Okay, no one's going to watch DuckTales, so I'm going to assume you're not my friends. Anyway, back to this. Now, we haven't covered how to do hypothesis test like the way that I am about to show you. But this should still visually, zooming back, this should still visually make some sense here. Let's see. Oh, you know what? Blast. Priscilla, you were correct. It was a P. I was wrong. I'm going to erase that. Totally not erased. My shame is still up there. Here's the thing. I don't know why. I'm sorry, let me rephrase. I know why I temporarily thought it was a mu. I know why. I was thinking birth weight. I was thinking that they were actually measuring the birth weight for this particular problem. And if they were measuring birth weight would have been a quantitative piece of data, making it a mu. But I'm sorry, you're absolutely correct. It was a P. Because they were separating the women into two categories. Two categories of having birth weights less than 6.6 and birth weights more than 6.6. Then, after they separated the women into those two categories, they figured out the proportion of those women who suffered from depression. You are absolutely correct. So, I got to rewrite this thing. Let me do the same thing, but let me put a P there. Again, it may seem like a silly thing here to be like, well, you just erased all of that to write the same thing. No, I erased all of that. Whoa, that is really light. Can you all see that? Or is that really light for you? I'll find a better pen. Ooh, colored pencil. There we go. But the reason is very important because when you are doing a null and alternate hypothesis, we need to make sure that we have proper notation. Proper notation, meaning you're using population parameter notation and that you are either using mu or P in the proper way. And yeah, I did mu because I thought, 6.6 has got to be quantitative. Oops. Is what happens when I think too hard. Smoke comes out my ears. Anyway, the null hypothesis is there is no difference. The null hypothesis is there is no difference between the two groups of women. That's what you have to kind of visualize. The null hypothesis is there is no difference, and because of that p-value, we would reject that. So, explaining context what the reported p-value means. It means there is a 2.48% chance of seeing the study's sample results given, can't say there is, given that there is no difference between the two groups of women. Or I should say there's no difference in depression rates between the two groups of women. Yeah.
You have to establish which group you want to do.
Well, here's the thing. I didn't actually have to write that. That's not required by the problem. I just did that for myself so that I can kind of visualize, oh, snap, I'm assuming no difference between the two. But if you wanted to, that's perfectly fine. You could, you know. In fact, because I'm doing greater than 0, I would surmise that group 1 or subscript 1 are the women whose birth weight are less than 6.6, because they, according to the study, experienced more rates of depression. But yeah, that's what a p-value is in context. Give it context. Give it context. Oh, this looks familiar, he said sarcastically. I'm not going to spend a lot of time on this one. I am simply going to point to the comments that I left on the minor for you guys on this problem. By all means, if you do have additional questions on this trucker problem, please message me about that. But I had changed the numbers. If you haven't actually noticed, I changed the numbers that were on this problem and actually reworded it based on what I kind of wanted to do. But I kept the essence of the problem the same. I would point out one thing, though. If you're going to do a 95% confidence interval, that would be a 1 prop Z interval. The Z implies what type of distribution? The Z implies what type of distribution? Normal. This implies a normal distribution. Tell me, where in the problem did it ever tell you to assume normality? You're shaking your head. Why? It doesn't. Meaning, you would have to go through assumptions and conditions in order to show that you are allowed to assume normality. And once you are allowed to assume normality, then you can use a 1 prop Z interval. See, over here, where is it? Pumpkin pie, number 13. Where am I? There I am. It said the contents of the cans are normally distributed. Oh, happy day. We don't have to, that's why I said, thank you, paper, for telling me it was normal. Now I don't have to do it, and I can move on with the rest of the problem. But for here, they didn't tell you. It implies a normal distribution. You have to show assumptions and conditions. That is done in order to show that you can actually use it. So again, please look back at the comments that I left you on that minor. Let's see what we got up. Wait, what the heck? What is this? Oh, okay. Random emails coming in. Let's take a look at number 16. I hope we do have time for this. We probably do. Again, just a reminder before I do this problem. Thursday, assuming that I am not here, there will be something for you to do in Google Classroom. It will be something that will help you get prepared more so for this major assessment that I'm going to be throwing at you. So please make sure that you have everything good to go. For those of you that are online right now, there will not be a live stream on Thursday, assuming I am not here, but you will get that announcement in Google Classroom. So you won't be just left in the dark. But you still have to do something during my class period, of course, in order to get credit for attendance. Tax advice. Y'all file your taxes yet? You did? Good. Nice. Nice. See, I got a house and 2 kids. I got a lot more than that. No, but I filed mine in the beginning of February. You really should get in the habit of doing that. You get your refund, as you can attest to, a lot faster. Yeah. Anyway, back to this. Each year, people who have each year, people who have income file income taxes or income tax report. That is such an awkward sentence. I'm sorry. People who have income, they file income tax reports with the government. Okay. In some instances, people seek advice from accountants and financial advisors regarding their income tax situations. Their advice is meant to lower the percentage of taxes paid to the government each year. A random sample of people who filed tax reports resulted in the data in the table to the right. Okay, hold on. Let me look at this table real quick. Did they pay lower taxes? Yes or no? They had tax advice? Yes or no? Okay. Does this data indicate that people should seek tax advice from an accountant or financial advisor, test an appropriate hypothesis, and state your conclusion? Interesting. Okay. So I am going to say, they want to know whether or not getting tax advice helps. So let's separate it into either they got tax advice or they didn't get tax advice. So I am going to make a null and alternate hypothesis that looks like this. The proportion of those who had advice versus the proportion of those who had no advice. Again, that's just a notation that I'm putting on there. You can indicate it differently if you wanted to. You could do 1 and 2 if you wanted to. But for a null hypothesis, I am going to assume there is no difference between the two. There's no difference. Nothing's going on here. It doesn't matter if you get advice or you don't get advice. I'm assuming there is no difference. Versus the alternate hypothesis. Now, mind you, the alternate, I shouldn't put that just yet, but the alternate is based on the question. They want to know, does it indicate that people should seek advice? Well, if they got advice and got more money back or had lower taxes, the proportion of those who got the advice getting lower taxes, I am going to have to put a little indicator to the side here real quick, but I will do that in a moment. It should be greater than 0. Yeah. I'm going to put a little note here because this is context. Put a little note here. The proportion of people who got advice, it's not exactly like, oh, they got advice and versus they didn't get advice. It's paid lower taxes with advice versus paid lower taxes without advice. Just to be very clear, that's what I'm indicating the two groups are. Both groups paid lower taxes. It's the proportion of those who paid lower taxes. But the first group is with advice, and the second group is without advice. I am running a little short of time. What I'm going to do, I'm going to try and get through as much of this as I can, but I'm not going to rush. I'm not going to rush, but I will provide the answer key for you guys I will provide the answer key for you guys through Google Classroom, just so whatever I don't get through, you'll at least still have it. But let's see what we can do here. This would be my null and alternate hypothesis. Ultimately, I would love to do a 2 proportion z-test, but first, I gotta go through some assumptions and conditions. According to the most recent assessment that we took, assumptions and conditions seems to be the part that we are stumbling over the most. Seems to be. Either people are skipping it entirely, or they are only doing it partially. Some of you are doing it completely. But most people are either just skipping it or doing part of it. So we can go through it one at a time. It says it's a random sample within the problem. So I can say random sample stated. It's stated within the problem itself. I even underlined it. You can't see where I underlined it, but I did. All right. How many people were sampled? It says a random sample. Okay. Well, let's see. How many people had tax advice here? It looks like 19 and 86. Oh, you can't see it. 1986, that makes 105. And 48 and 24, that make 72. So those are my 2 samples, if I split it like that. The proportion with advice versus not advice. I could say that 105 and 72 are large enough samples. I could say 105 and 72 are less than 10%. 10%. Well, actually, you know what? I could probably do this separately. Yeah, I'm gonna put it together in one statement, but I'm gonna use the word respectively. Okay. Less than 10% of people who got tax advice and didn't get tax advice respectively. I say respectively because 105 represents those who did get it and 72 represents those who did not get it. Now, we would still have to do success and failure. And now, again, I'm running short of time, so I'm just going to verbalize this, and I'm going to wrap it up there, and I am going to give you the answer key on Google Classroom. But if you're going to do the successes and failures, you are going to have to talk about all 4 of these numbers within the table. And all 4 of these numbers are greater than 10. But, again, indicate that. Write out the sentence in that sense. Like, you could say, 48 is greater than 10 failures, if that's the failure part. 24 is greater than 10 successes, if that's the success part, etc. I hate running out of time. I would have 24 more minutes if this were a real day. Ooh, we might be going back to that, right? Sweet. Yeah, right around the time we're just going to be reviewing for the stat test. Anyway, I am going to post that online. I will have instructions for you for Thursday. Please make sure you're bringing your Chromebook fully charged, ready to go, because that's where you're going to get this information. If you haven't left a comment in the chat, please make sure that you do. And there's the bell. I was almost there. See you guys. Bye-bye. Oh, I might not see you guys till Monday. So, wow. Crazy. See you guys.